Hello, welcome to another module of this course, Analog Circuits. We are now in the week 4, and in the previous module last week we had covered about feedback, the various effects of feedback like gain desensitivity, bandwidth enhancement, increase in linearity. In this module, let us see an example of feedback that is applied to a circuit. Suppose we have a circuit like this, now the circuit, this is with feedback, and the circuit without feedback is like this. So, after feedback, the only difference between this circuit and this circuit is this additional resistances R1 and R2, which are connected like this. Now, what is the impact of these resistances on the overall performance? First, note that here we are tapping the voltage at the output and feeding it back to the input. At the input, when we feed back, what is happening is some portion of the input voltage that should have been applied directly is being subtracted by an amount equal to this voltage, or by an amount equal to the voltage appearing across R1. So, this is an example of what we call voltage feedback. It is a negative feedback, but the type of negative feedback is voltage. Okay. So, then what do we see? What we see here is the output voltage V0 is given by mu V1 upon RL plus R0 times RL, which in turn is equal to mu Vs RID upon Rs plus RID times RL upon plus R0. So, this is my expression without feedback. Okay. Now, with feedback, my output voltage is given by an expression which is like this. And this N is given as like this. Now, another effect of feedback which I did not discuss in the previous module was that the output and input impedances, depending on the kind of feedback that is provided, the output and input impedances are also modified. So, for a voltage amplifier, as you know, output resistance or impedance as low as possible. Why? And input resistance or impedance as high as possible. Why is this? Because if we go back to the model of a voltage amplifier, so in a voltage amplifier we have a voltage dependent voltage source, an input voltage V in with input impedance R in, and output impedance R0, and output voltage is V out. Now, the reason this R in should be as high as possible is because we want the entire V in to appear at the input. Okay. Actually, I should have mentioned. So, this is V1 is the voltage that is actually appearing in the inside of the amplifier, removed from R in, and the voltage dependent voltage source produces an output mu V1. Okay. This is proportional to V1, this voltage V1. If Rin is not very high, then there will be some current flowing through this Rin, as a result of which the entire Vin will not appear at V1. On the other hand, if Rin is very high, then no current will flow inside Rin, and therefore, the entire voltage Vin will appear at the input. For the output, however, the scenario is different. Here we want this mu V1 to appear completely at the output. So, to appear completely at the output, it should face as less potential drop across this R0 as possible. In other words, this R0 should be as low as possible. Okay. Let me take a different example of, suppose we have what is called a transconductance amplifier. I at output, that is current output, and V at input, at voltage input. So, for this transconductance amplifier, I should not short this, actually it should be like this. Yeah, I would like to correct the previous figure here. It should not be shorted, it should be open. So, this is open. So, it is like this. I mean open, short, basically this is the part where it is actually the voltage is being applied to the amplifier, and for a transconductance amplifier we will get a voltage dependent current source. Okay. Now, for a current source, the output impedance is given as R0. Okay. So, this is V in and this is the output current I0. For this case, however, the input conditions remain the same, that is R in as high as possible, but this in this case R0 should be also as high as possible. The reason being, we do not want any part of this current source, the current produced by this current source, to leak into this R0. We want all of that current to go to I0, hence R0 should also be high. So, here we just disgraced a little bit about how what kind of output impedances should be there for a voltage amplifier, voltage input, voltage output amplifier, and a transconductance amplifier. Now, I leave it as an exercise for you to find out what should be the input and how high or how low the input impedances of an ideal current amplifier and a trans resistance amplifier should be. So, for a current amplifier, the input is current, output is current. For a trans resistance amplifier, input is current, output is voltage. So, I leave it as an exercise for you to find out what should be the ideal values of the input and output resistances of such amplifiers. Now, coming back to the voltage amplifier that we are studying. So, we should have the Ri as high as possible and Ro as low as possible. It can be shown that this Rif with feedback, the input impedance becomes like this and the output impedance with feedback becomes like this. As you can see, the input impedance with feedback is now significantly higher as compared to what was there initially, and the output impedance is now significantly lower than what it was initially. Okay. So, this is also one impact of feedback, that we see that for voltage amplifiers where we apply voltage out, we tap the voltage at the output and feed it back as voltage to the input impedance increases, the output impedance decreases. Or for a transconductance amplifier, what we will observe is that where for a transconductance amplifier, of course, we are taking current from the output and feeding it to the input as voltage. In that case, we will observe that the output impedance increases upon applying feedback, and the input impedance also increases upon applying feedback. So, in this module, we covered a sample analog circuit, which was given a feedback of voltage feedback, that is voltage from the output was fed back to the input as voltage. What we observed is, first of all, the general feedback gain. We got a gain expression where with the feedback factor present, and since the feedback factor was present, therefore, we would also get the other effects that we discussed in the previous module, namely gain desensitization, increase in linearity, increase in bandwidth. And in addition to that, we also observed another effect that we had not discussed in the previous module, that is the output impedance of this voltage of this amplifier with voltage feedback, the output impedance decreases and the input impedance increases. So, in this module we shall end here. In the next module we shall start with stability. Thank you.